All right, so in the last class, we talked about this concept of charge. We talked about that I can use the term charge as a noun or a verb. Charge can be something that an object possesses. We know electrons possess negative charge, protons possess positive charge. But when we talk about charging, usually we mean that term used as a verb. Charging is what happens when electrons are transferred from one place to another. So we talked about the concept of charge and charging, the fact that when you charge something, there must be a transfer of electrons. As a matter of fact, your lab, you did a lab and it dealt with charge and some of the concepts that we talked about. And hopefully that made things a little bit more clear when you went through the lab. But really what we're trying to do here is we're trying to answer the question, what is voltage? What is current? What is resistance? So we needed to understand a little bit about charge before we can actually address those questions. So let's get into the details of that. And today I want to answer the question, what is voltage and what is current? And resistance we'll handle when you guys come in for lab. And speaking of lab, your first face-to-face lab will be Tuesday, this coming Tuesday. Now I'll put up some information on Blackboard so you know, number one, when to come in, what time, the room. You want to make sure when you come in next Tuesday that you have a mask. We can't allow anybody in the lab without a mask. And you want to bring your digital multimeter with you. You've had hopefully a couple weeks to get that. So you want to have that by next Tuesday. As far as work that needs to be handed in, anything that was uploadable on Blackboard, you're able to upload, you can do that. Anything else you'll bring in on Tuesday. And so what I'm going to do in the next day or two, I'll put up just kind of a list of what should have been uploaded to Blackboard and what I expect you to bring in on Tuesday. Any questions regarding that, just hang on to the end of class and I'll be happy to stick around and address the questions. The other thing, the other thing before you start, go ahead and text me if you haven't done so. Our attendance is due tomorrow. We have to turn it in tomorrow. So your name has to go in at least one time in the first 2 weeks of class to be considered here. So I think most everybody has sent me a text before, but if you didn't send me a text and you don't do it today, and even though you've been here, they're going to count you as not being in class and you'll be dropped from the course. So make sure you, important, text me, put EET 101 in there, first and last name, and then that should be it. So go ahead and send that. And we'll get started. So as I said, in the last class, we talked in detail about the concept of charge and the fact that when you want to charge something, there must be a transfer of electrons from one place to another. The other thing we talked about was amount of charge. We said that when you buy a carton of eggs, 12 eggs in that carton. You buy eggs by the dozen. When you buy a pack of cigarettes, there's 20 cigarettes in that pack. You buy cigarettes by the pack. Well, when you have electrons, you package electrons in something called coulombs. And if you have 12 eggs, you have a carton or a dozen eggs. If you have 20 cigarettes, you have a pack of cigarettes. If you have 6.25 times 10 to the 18th electrons, you have 1 coulomb of electrons. And so coulombs are the way we kind of think about electrons. Now I'll talk about individual electrons, but it's really impossible to operate or to consider or do anything with 1 electron. It's just not physically possible. So we think about groups of electrons. We think about coulombs of electrons or coulombs of charge. And so I gave you this relationship here. 1 coulomb, 6.25 times 10 to the 18th electron. That's something that you want to remember, the coulomb of charge. So let's talk about voltage. Let's talk about voltage. And to do that, to talk about voltage, I want to relate it to something that you already know about. I want to relate it to gravity. Gravity. Voltage is actually related to gravity. I shouldn't say it's related. There's an analogy between the two. So you know that if I have an object, and let's say this is just a container, it's not really heavy, but let's say it was a really heavy container. Maybe it was made out of lead or some kind of metal, solid metal. And if I hold it out like this, it's going to feel like it's pretty heavy. What I feel when I hold it out like this, I feel the weight of this. I feel the weight of this object. Now, what is weight? Well, weight is really the Earth's pull on the object. Well, how does the Earth pull on the object? The Earth pulls on the object because gravity exists, and gravity, this is in the gravity field, or gravitational field, and gravity, the forces of gravity is actually able to transfer or to move through the field, somehow connect with the object and pull down on it. And I know if I release this, gravity will pull it all the way down to the ground. And so when I do this, when I take this object or mass and I move it from here to here, it now has what we call potential energy. Potential energy is energy an object has because of its position. So you might have studied this in physics in another class, but basically there's a potential energy that this has because of its height. And so if I want to give this object more potential energy, all I got to do is I can raise it up higher. The higher it is above some starting point, the more potential energy it has. And so I can talk about it like this. I can say there's a gravitational potential between the starting point and this point. Now, if I put this back at the starting point, there's no gravitational potential between this point and this point. There's only gravitational potential between this point and another point when I move this up. There's a potential between this point and this point, the potential to do work. Now, what do I mean by the potential to do work? Well, once I move this up and give it potential energy, if I let it go, what's going to happen? Well, it's going to fall, and as it falls, it's going to speed up, and now it has a different kind of energy. Here it has all potential energy. When I let it go, it's going to speed up, and it's going to get lower and lower and lower while it's speeding up, so that the potential energy is becoming more and more energy of motion, or more kinetic energy. Right before it hits my hand, I have all kinetic energy. But I started with potential energy. There's a gravitational potential difference between this point and this point. Well, it turns out I can do exactly the same thing with charge. Just like I can separate the mass from my hand, and it has a potential here, a gravitational potential that I can turn into work by dropping it, I can do exactly the same thing with charge. I can take two charges and I can separate those two charges. I can separate them. If I separate the two charges, I have exactly the same situation that I had when I had the mass. I can take the mass in my hand, I can separate the mass from my hand. There's a gravitational potential difference between this point and this point, or I can take two charges and I can separate them, and there's a potential difference between these 2 points, between these two charges, but not a gravitational potential. There's an electrical potential difference between the two, because we're dealing with electricity here, electric charge. And just like I can take the mass and separate it from my hand, if I let this go, it's going to want to move this way. And so I have all potential energy here. When I let it go, it's going to get lower, which means the potential energy is decreasing, and also it's going to speed up, which means the kinetic energy is increasing. So you might remember that the conservation of energy principle says energy cannot be created or destroyed. It can only change from one type to another. Energy cannot be created or destroyed. We can only change it from one type to another. And so in the situation I'm describing here, I can give this potential energy by moving it up from starting point to here. So now it has gravitational potential energy. I can change that gravitational potential energy to kinetic energy by just letting it go. If I let it go, now this thing is moving, and the potential energy is decreasing, but at the same rate it's decreasing, the kinetic energy is increasing. So I can make it move just by putting it in the gravitational field, have a gravitational potential difference. Well, again, I have exactly the same thing here. If I separate these, now there's a potential difference between the plus and the minus charge, not a gravitational potential difference. There's no gravity here. There's an electrical potential difference between the two. And just like with the object I was holding, if I let this go, you know, like charges repel, but unlike charges attract. If I let this go, these charges are going to move. They're going to want to come together. They're going to move. So if there's motion, all the potential energy here, as they move together, is becoming kinetic energy to the point to where they get together. And so I can have a gravitational potential by taking mass and separate it. And if I let the mass go, I turn it to kinetic energy. Or I can have charge and separate it, and I have a potential difference, but not a gravitational potential difference. We call separated charge an electrical potential difference or voltage. Voltage. So I said a whole lot there. So what exactly am I saying? What I'm saying is that all voltage is, when you talk about the voltage of a battery, or the voltage of the wall outlet, or voltage in any way, all voltage is a separation of charge. All voltage is a separation of charge. If you want to create voltage, all you got to do is separate charge. Voltage is a separation of charge. Well, what happens when you do that? What happens when you separate charge? Well, what happens when you separate mass? If I take this mass in my hand and I separate it, I develop a potential difference between this point and this point. Again, not in this case, it's a gravitational potential difference because I'm talking about weight and gravity. This thing has energy stored in it, potential energy, and if I want to change it to kinetic energy, all I got to do is let it go. And when I let it go, this thing's going to move, and now that it's moving and speeding up, the potential energy is becoming more and more kinetic. The thing about kinetic energy is this, and this is important. The thing about kinetic energy is the only kind of energy that can do work. Kinetic energy is the only type of energy that can do work. Potential energy cannot do any work. It's stored energy. You release that energy by changing the potential to kinetic, and kinetic energy can do work. For example, let's say that I had you might have seen this when they're building buildings. They might have a big metal pile, big metal bar, and they'll have a crane, and they'll drop this off the crane, and they'll hammer this into the ground, a stake into the ground. I can use the kinetic energy from the falling mass to do the work of hammering a steel rod into the ground. Kinetic energy is the only energy that can do work. In order for work to happen, something has to move. If there's no motion, there's no work. And so I have exactly the same thing here. Just like I can take the mass, I can separate it. I have a gravitational difference now between this point and this point. I can let this go, and now I turn the potential energy into kinetic, and the kinetic energy of this thing falling can do work, the work of driving the stake into the ground. I can do exactly the same thing here. I can separate charge, and once I have charge separated, I have potential energy stored in this system. Not gravitational potential energy. There's no gravity here. The thing that wants to pull this down is gravity. But the thing that wants to pull these together is not gravity. It's the fact that, unlike charges attract, there's an electric force that exists between these two objects, whereas there's a gravitational force that exists between these two objects. So here I have a gravitational potential difference. Here I have an electrical potential difference. You call this a gravitational potential difference. You call this an electrical potential difference or voltage. So when you use the term voltage, all you mean is this charge has been separated, and that separated charge now has potential energy or voltage. Once you have a voltage, what I can do is if I want to make work happen, something's got to move in order for work to happen. You got to give it kinetic energy. Well, how do I give this kinetic energy? I just let it go. It's moving now, so it has kinetic energy. Kinetic energy can do work. I can do exactly the same thing here. If I separate these charges, unlike charges attract, they're going to want to come back together. These two charges are going to move together. And in moving, I'm changing the potential energy that is stored between these two separated charges. I'm changing that potential energy to kinetic energy, and now the kinetic energy can do work. So voltage is a separation of charge. Write that down. Voltage is a separation of charge. Pretty easy definition, but it took all of this time to get to that, to where you can understand the concept of charge, and how I might relate in a situation like this. Now, if voltage is a separation of charge, how do I take that voltage, that separation of charge, or that electrical potential difference, how do I take that and turn it into a current? How do I do that? Well, let's just talk about that. So I want to start by saying there's a cause and effect relationship between voltage and current. The cause of a current is a voltage. This is the cause, this is the effect. It takes a voltage to make a current, not the other way around. So if I want to make a current, what I have to do, I have to first start with the voltage, and I can use that voltage to make a current. Well, let's talk about what is current. What is current? Well, what is any kind of current? If I have, imagine I have a pond, just water in a pond. The water's sitting there, and the water's not moving at all. So I just have static water. I have water that's not moving, I have static water. If gravity pulls down on that pond, I have a stream, right? I can get the water to flow downstream. And now I have water that's moving, so I have water currents. If I have just the pond, the static water, and the water's not moving, and I put a boat in it, we'll assume the wind's not blowing or none of that. If I put a boat or a leaf or something in the pond that's floating there, if there's no water current, no work can happen on the leaf or the boat. It's just going to sit there. If I put it in a stream that has current moving, water moving, then that water can do the work of taking the leaf or the boat and moving it downstream. So if I have static charge that's sitting there, it can't really do anything. But if I can some kind of way make the charge move, now the charge has kinetic energy, and the kinetic energy can do work. So how do I make charge move? Well, how you make anything move? You start with something that's not moving, and you got to push it. The problem is we can't push electrons. There's no way to push electrons. Let's talk about force. Now, most of us know the term force, and you might define it a lot of different ways. But the easiest way to describe force is a push or pull. Anybody can understand that definition of force. A force is a push or pull. But there are actually, in the universe, two kinds of forces. There are two classes of forces. The first class is called a contact force. A contact force. The second class of forces is called, has a long name, it's called an action at a distance force. An action at a distance forces. So I have two classes of forces. I have contact forces and I have action at a distance forces. Let's talk about contact forces. So a contact force is exactly what you think it is. I need something some kind of prop, but there's nothing in this room. I'll use this eraser. A contact force is exactly what you think it is. I have an object and I have another object. Now, Newton, the physicist Sir Isaac Newton, he's the father of the force stuff. He came up with a lot of the math and understanding we have about forces. And Newton had these three laws, Newton's laws, really famous ones, but the one I want to talk about now is Newton's third law. And people usually, they'll quote Newton's third law and use it outside of physics, and they usually say it the wrong way. What people say when they quote Newton's third law is they say that for every action there's a what? For every action, there's an equal and opposite reaction. So that's a statement of Newton's third law. For every action, there's an equal and opposite reaction. But really, that's not what Newton said. That's not even what he meant. What Newton said was this. He said for every action force, there's an equal and opposite reaction force. For every action force, there's an equal and opposite reaction force. That's what he said. Now, what does that mean? Well, said another way, what Newton said, what he meant was, it's impossible to have a single force. Forces always exist in pairs, in twos. And so if I think about it, let's say I push on the board. If I push on the board, there's two forces. Force number one is the force of my hand on the board. Force number two is the force of the board on my hand. Force number one, the force of my hand on the board. My hand is pushing on the board. Force number two, the force of the board on my hand. The board is pushing back on my hand. You can never have one force. And so these contact forces, I have two objects. Eraser, my finger is another object, and these can touch, and there's two forces here. There's the force of my finger on the eraser, that's one force. There's the force of the eraser on my finger, that's the second force. So I got the two forces. Now if I increase the force, eventually the force of my finger on the eraser is going to overcome friction, and this thing is going to move. I can make something moving by just pushing it, but in doing that, the two objects, namely my finger and the eraser, they're touching each other. Things or forces travel from one object to another in this way a lot, when you have two objects touching each other. That's called a contact force. Unfortunately, I can't do that with electrons. See, what I want to do is take, like I have water that's not moving, and I want to turn it into water that's moving, because if I have water that's moving, it can do work. It can do the work of moving a boat, floating a log downstream. If something's moving, it can do work. I want to take charge that's not moving, and I want to push it some kind of way, and turn it into charge that's moving, i.e. electric current, and then once the charge is moving, it can do work. The work of lighting up a light bulb, turn your cell phone on, whatever you want to do, it can do work. So how do I take electrons and make it move, make them move? Well, I got to apply a force, but I can't apply a force like this. There's no way for me to take electrons and push the electrons. I can't do that. So nature actually gives us a whole nother class of forces. And these forces are called action at a distance force. An action at a distance force. The name says exactly what it is. So what is an action at a distance force? Imagine if I had the eraser and I had this object here, and my finger never touches the eraser. Imagine a situation where I just get close to the eraser and the eraser moves away. Some kind of way, the force from my finger is transferred to the eraser, and the eraser moves away because the force is a repelling force, but the finger and the eraser never touch each other. The action happens through a distance. Do these kind of forces really exist? Can anybody think of a situation that you might have seen or dealt with where you have two objects and you move one object over, and the second object and the first object never have to touch each other, but the first one moves away? Can anybody describe a situation like that? Have you seen something like that before?
You put magnets together?
Exactly. Everybody's done that. Imagine I have two really strong magnets. The way magnets have poles. Charges have polarities, a plus polarity, minus polarity, but magnets have poles. So if the cap is a north pole and the other end is a south pole, if I take a north and a north, they repel. If I take a south and a south, they repel. If I take a north and a south, they attract, they stick together. You've all played with magnets, you've done that. Imagine I have two really, really strong magnets on a smooth surface. Imagine I have two really, really strong magnets on a piece of really smooth glass, and I slowly move one magnet over to the other. If I have magnets that's strong enough, and if the surface they're sitting on is smooth enough, what will happen is this one will move away and they never have to touch each other. That's pretty cool. That's what we mean by an action at a distance force. One type of action at a distance force, one type is the magnetic force. You've seen that with magnets. Magnetism is an action at a distance force. Can somebody tell me another situation where you have two objects and the two objects never have to touch, but yet they can exert forces on each other? The one that's closest to you is probably the magnet, but there's another one. Give me another example. if I have this object, somebody just sent a text. Yep, somebody was Alberto. He said gravity. And that's exactly what I was going to talk about. Now, if you hold this up and you let it go, you know it's going to fall. And if you ask a kid, well, okay, kid, why does it fall? They're going to be like, well, I don't know, because that's down. So if you think about it, the earth is a sphere, and there is no up or down. It's all relative. I mean, you can be here. This could be you. This could be you. Or this could be you. We're living on a sphere. So there is no up or down. Everything's just relative, right? The reason this falls is not because there's up or down. What if you were down here on the South Pole? Down is this way, but the object would still fall that way. So there is no up or down. The reason things fall is because the earth is pulling down on it. It moves this way. It moves, if you're here, that way. If you're here, that way. If you're on the South Pole, it moves that. The reason things move towards the earth is because the earth is pulling on the thing that you drop, just like the two magnets are pulling each other to come together or move apart. There's actually a force, in this case, a force of attraction between the object and the earth. Remember what Newton said, though. Newton said you cannot have one force. There's always two. So there's the force of the earth on the object, and there's the force of the object on the earth. I don't know if I said the same thing twice. The earth is pulling down on the object, and the object is pulling up on the earth. Always have two forces. Now, it's silly to think that the earth's going to come up and meet the object, because the earth is so much bigger than the object. I mean, the object here on this diagram is just a dot. And so the earth's not going to come up to the object's going to come down to meet the earth. The point of it is that there's a force pulling this thing down, and that force is not, I don't have the earth in contact with the object. Some kind of way that force goes through a distance and pulls this down. What does it go through? Well, there's gravity involved. So the other force, action at a distance force, is gravitational force. It's gravity. So we got magnetism. That's an action at a distance force. Magnets don't have to touch each other for one to exert a force on another. There's gravity. That's another type of action at a distance force. If I have things that have mass, like the earth and this object, they don't have to touch each other for the earth to pull down and to make the object fall, for the earth to exert a force on the object. There's one more, though. There's one more. Can anybody think of the final example of an action at a distance force where I have two things and I can bring them close together and one can exert a force on the other without them touching each other? And if you did the lab, that should be a big hint to you. I know you all did the lab. I like when you guys don't answer. It gives me a chance to sit down and rest. So what is the third and final way of producing an action at a distance force? You know, I think it's kind of cool. I was looking at myself on the video when I sit like this and look at the board, and I can see the camera over my shoulder. So it looks like I'm looking at what you're looking at. I can also see how fat I am. I need to lose some weight. That's the problem with being on video, but that's not why you're here. Let's stay focused. Can anybody tell me the last and final action at a distance force? You did the lab. What is it? You guys did do the lab, didn't you? Did you do the lab? Make sure I'm not cut off. Let's see. Amber, did you do the, who's that, Amber? Amber, did you do the lab?
Yeah, is it polarization of the charges?
Yeah, charge. You know from the lab And just from a discussion, if I have positive and negative charge, if I have like charges, if I have plus and plus, they push apart. If I have minus and minus, they push apart. If I have plus and minus, they pull together. Then you do the thing with John. I kind of liked it, John Travolta, where or the balloons were even better example. You rub the balloon, and you can stick the balloon to the sweater, or you can take the balloon and put it on the wall. But if you look at the charges, you saw when you put the balloon on the wall, those charges were pushed, the negative charges were pushed away. Because in the wall is a type of dielectric that allows the charges to be polarized. So you looked at that lab, and hopefully you understood that. So the point is that electric charge actually can exert forces through a distance, and we call that kind of force the electric force. Electric force. By the way, the electric force is also called a Coulomb force. It means the same thing. In physics, electric force and Coulomb force are the same. So remember what I'm trying to do, because I know I'm saying a whole lot. What I'm doing is simply this. I want to take electrons which are not moving and change them to electrons which are moving. Why? Because electrons in motion, that's called electric current. And in nature, if something's moving, that's the only kind of something that can do work. So I want to make the electrons do work, therefore I have to move. So to do that, I got to take electrons that are not moving and some kind of way apply a force. But I cannot apply this kind of force. I can't touch electrons and make them move. So how do I do it? Well, that's what we're trying to answer. Now, I have one more question for you. Just think about this. I have magnetism. That's an action at a distance force. I have gravity. That's an action at a distance force. And I have the electric force or Coulomb force. That's also an action at a distance force. I have three different action at a distance forces. What do all three have in common? They all have one thing in common, and I'll tell you what it begins with. It begins with the letter F. They all have one thing in common, and the thing they have in common begins with the letter F. What word begins with the letter F that all three of these have in common? I should make this one of those tests where if you get it, you don't have to take the course, you just get an A, and you can forget all the work and exams and quizzes you got to do for the next 13 weeks, 12 weeks. But they won't let me do that. What does magnetism, gravity, and the electric force, what do they all have in common that begins with the letter F?
Friction.
Good guess. Well, that's not it. I'm going to give you a hint. I know when I give you this hint, you're going to get it. I was trying not to give you this hint. You play sports on it. You guys better get this. You play sports on it. I can't wait to meet you all next Friday. If you don't, you play sports on it. Yes. Who was that? Was that Amber?
Yeah.
Oh, come on, man. Come on. You had to get that. I'm gonna say when I'm gonna laugh. I'm gonna laugh at you guys when you come up here on Tuesday. If you didn't get a field, a baseball field, a soccer field, there is a magnetic field between two magnets. There is a gravitational field between two objects. When you send a rocket ship up, when they launch a rocket ship, they're trying to escape what? The Earth's gravitational field. And then there is a field, you don't know it, but there's an electric field between charges. So what is a field? Well, to be honest, we don't know what a field is, but we know how it acts. Fields, whatever it is, a field, a gravity field, an electric field, a magnetic field, it allows force or energy to travel through a distance without any medium. Only the wire, only air. Fields, they're invisible. Whatever they are, they allow force to move from here to here or energy to move from here to here through that field. And so I can actually exert a force on something if I put the something in a field. If I put it in the gravitational field, a force can be exerted on this to make it move down. If I have two magnets, and there's a magnetic field, that magnetic field, I can take a paper clip, I can take a single magnet and put it over here near the paper clip. I don't have to touch it. I can just bring it here and let it go, and the paper clip will snap over to the magnet because I put the paper clip in the magnetic field of the magnet. The force travels through that field. And finally, if I have charge that's separated, I have an electric field. So anything I put in that electric field, any kind of charge, that field can actually exert a force on that charge and make it move. So if I want to make current, I start like this. I got to start with a voltage. And all the voltage is charge that's separated. So I take and I separate charge. So here I have some plus charge, and here I have some minus charge. Now, if I have two magnets, so I got a north pole and a north pole, there's a field that exists between these. And if you put a paper clip in that field, it'll experience a force and either go to that magnet or that magnet. Well, when I take charge and separate it, there's also a field that exists between the separated charge. So I first take charge and separate it. Remember, separated charge is called an electrical potential difference or voltage. So now I produce a voltage. And in the region of that voltage, in the region of that electrical potential difference, there's a not magnetic field, not a gravitational field, there's an electric field. And just like when I put the object in the Earth's gravitational field, the field can pull down and make it move. If I put an electron in here that's free to move, like charges repel, so these down here, the force is pushing it that way. And at the same time that these like charges are pushing this away, unlike charges attract, so these forces here, this is pulling it. This has no choice but to move this way. And now I have an electron that wasn't moving. When I let it go, it's going to move from negative to positive. That electron now has kinetic energy. And if the electron is moving and has kinetic energy, we call that moving electron electric current. And because the electrons are moving, they have energy, kinetic energy, and kinetic energy can do work. That moving electron can do the work of lighting up a light bulb. That moving electron can do the work of turning your cell phone on. That moving electron can do the work of nuking something in the microwave. Whatever the circuit is designed to do, it takes electrons that's moving, it takes electrons that have kinetic energy to do whatever kind of work the circuit is designed to do. So, voltage is a separation of charge. I start there. I got to separate charge. Well, how do we separate charge? Well, right now, you probably know two ways. Number one, I can get a battery. A battery separates charge. When you look at a battery, your car battery, if this is your car battery, your battery has a terminal here and a terminal here. One terminal is marked positive, the other terminal is marked negative, or one terminal might be red in color, and the other one might be black in color. You got two terminals. What is the meaning of the plus and minus terminal? Well, the meaning of the plus and minus terminal is all that battery is doing is separating charge. Or you might get voltage from your wall outlet. Now that's a little different because that comes from a generator, but generators do exactly what batteries do, they separate charge. What about when you have the light, you know, the lights you stick out in your front yard during the day, and the sun charges those up, and at night they light up. You never have to put a battery in them. I can use basically the photoelectric effect. That's something that Einstein discovered. But basically, I can use that solar cell to separate charge and give me voltage. I don't care what kind of voltage you call it, what you name it. All it is all the same stuff. It's charge that's been separated. Your phone charger, when you charge it up, your phone charger separates charge to create a voltage. And so I start by creating a voltage by separating charge. Once I separate masses, I have a field between the two masses called a gravitational field. Once I separate magnets, I have a field between the two magnets called a magnetic field. And once I separate charge, I have a field between the separated charge called an electric field. If I put a paper clip in the magnetic field, it can make it move. If I if I drop the object in the gravitational field, that gravitational field can make the object move. If I have an electron that's free to move, and I put that electron in the electric field, the electric field is going to act just like the magnets in the paperclip. It's going to cause the electron to move away from the negative towards the positive. Now I've moved that electron. I've exerted a force, not a contact force, but an action at a distance force through the E field, the electric field. Now the electron has kinetic energy. It's moving. So now we have electric current. So voltage is a separation of charge, an electrical potential difference. Current is charge in motion. It takes a voltage to produce a current. It takes separation of charge, voltage. Voltage is the electrical pressure to move the electrons. The cause of a current is a voltage. The cause of a current is a voltage. Now, any questions over that? I know I said a lot and I went kind of fast, but anybody have any questions? Because we got to deal with equations. We got to be able to calculate this stuff. So let's do some math stuff here before. I got like about 6 or 7 minutes. So let me give you some equations, and you have I think you have the supplementary quiz. This should help you out with that a little bit. All right. So by definition, voltage is work per unit charge. So what do I mean by that? Work per unit charge. Here's what I'm saying. Let's say I got some charge right here. Got some negative charge. Down here I got some positive charge. And let's say I have a single electron. I'm going to put it right here. I'm going to put that electron right here. And that electron is going to be really happy here because, you know, like charges repel, but unlike charges attract. So the fact that this is negative, electron has negative charge, and this is positive, this group of charges is positive, it's happy because unlike charges attract. But what I want to do is I want to move this electron from here to here. So I'm trying to take the electrons away. The positive charges are pulling on it because unlike charges attract, and these charges are pushing it away because like charges repel, and I want to try to overcome that repelling force. I got to really push that electron up. So I'm going to push the electron up from here to here. That means I got to do work. I got to do work moving it from here to here. But eventually, I get it there. Well, it turns out, instead of having one electron, remember what I said earlier? It's silly to think about moving one electron. There's no way. An electron is, and I love this word, an electron is infinitesimally small. Electrons are infinitesimally small, infinitely small. That's tiny. So there's no way to move a single electron, so we move groups of electrons. We move coulombs of electrons. So assume I have not one electron, but I have a coulomb of electrons, 1 coulomb of electrons. And I want to push those 1 coulomb of electrons from here all the way up to there. I got to do a lot of work to move all those electrons up this way. It turns out that if I use 1 joule of energy in moving 1 coulomb of charge, then the potential difference between these 2 points would be 1 volt of electricity. In other words, looking at this equation, work, the unit for work is the joule, charge, the unit for charge is the coulomb. What a volt is a joule per coulomb. That's equal to 1 volt. So I think the last 2 problems on the supplementary quiz deal with this concept right here. This equation, voltage equals work over charge. So you know the number of joules of work it takes to move the charge, and you know the amount of charge, how many coulombs of charge you have, you can get the number of volts where a volt is a joule per coulomb. All right, I accept that. And what about current? We said current is charge in motion. So how would you write that mathematically? Current is charge in motion. Well, current, and the way we show motion, when we talk about motion, we use something called a time rate. A time rate of change. And all that means is we have a fraction where the denominator of our fraction is time. So one example of that would be velocity. Velocity equals distance over what? Time. So velocity is a time rate. That means something's moving. So I can say that V equals distance over time. So you might say, all right, well, if I travel 100 miles in 2 hours, then my velocity or speed would be 50 miles every hour, approximately. So that's a time rate. Well, in physics, anytime you divide by time, it's a time rate. It means something's moving. And so current is a time rate. Current is how much charge passes a certain point in a certain amount of time. Going back to our example, if I have voltage, I have minus charge here, and I have plus charge here, and I have charge I'm going to move. I got 1 coulomb of charge. I want to move it that way. So I got a potential difference. I got to do work to move it that way. Well, what if I already have it moved up here? What if I already have it moved up there and then I let it go? If I let it go, I have like charges here, which is pushing this away. I have positive charges here, which is pulling it down. This 1 coulomb of charge is going to move this way. If I have 1 coulomb of charge move past a certain point, say this is my point. If I have 1 coulomb of charge, just 1 coulomb, move past a point in 1 second, if 1 coulomb of charge moves past a point in 1 second, then I have 1 ampere or 1 amp of current. So current, I can write it as current. Now, we don't use a C for current, we use an I. Current, I, equals charge, Q, divided by time, T. So here is an expression for current. Current is charge per unit of time. And what I was trying to show you here was that Q is, of course, measured in coulombs. T is, of course, measured in seconds. I'm dividing coulombs by seconds. So current has the units of coulombs per second. But if I have 1 coulomb per second, we define a coulomb per second to be 1 amp or ampere. So you can say I got 15 coulombs per second. That's my current. Or you can say I got 15 amps of current. It's the same thing. In this class, we'll write it this way and not that way. So there are 2 expressions. One for voltage, one for current. And I see I'm out of time. So we'll stop here, and then we're almost done with chapter 2, the chapter. I got one more thing I have to talk about. I got to talk about resistance. I'm not going to do that in class. I'm going to do that in lab. The first lab you deal with, we'll do a couple labs when you come in, but one of those labs will deal with resistance, so I won't worry about that this week. I do have to talk about the electric circuit, though. And it'll take me just a couple minutes to do that. So, you guys, I won't see you till Monday. You have a great weekend. Make sure you look at Blackboard. I'll be posting stuff up there, what you need to do, what you need to bring in for Tuesday. So make sure you look at Blackboard over the next couple of days. And you guys stay safe, and I'll see you on Monday. I will stick around. I have another class here in a couple hours. So if anybody has any questions, I'll be happy to stick around and answer any questions. But other than that, that's all I have for today, guys. I'll see you on Monday. Does anybody have any questions for me?
How do you confirm that you sent the text properly? So you don't get kicked out of the class.
That's a good question. What's your name?
Eric Mabrolas. I literally just sent it at the beginning of class.
Okay, let me look to see, Eric. Let me just look to see. Does your number begin with a 703?
Yeah.
Okay, I got you. You're okay.
All right, cool. I just didn't want to get kicked out without.
Oh no, you're good.
Well, have a
All
good
right.
one.
See you.
Hi.
A question?
Oh no. Hi. Hi, Professor.
Wait a minute. You're breaking up. I can't hear you. Your audio's breaking. Who is that talking?
That's Yusuf.
Oh, Yusuf, hi.
Yeah, hi. How you doing? Just for Tuesday, it's silly. If I wanna come early, just I come early. You will be there.
Yeah, actually Tuesday I'll be here on at 8 o'clock in the morning, and I'll
Okay.
be here. Yeah, I'll be here until from Tuesday. I'll be here at 8 a.m. to 10:30 p.m. So I got all day Tuesday. So if you're
Wow.
gonna come early, just send me a text, okay?
Okay. All right.
Just send me a text. Let me know you're coming early.
Okay. Thank you. I appreciate that.
All right, buddy. See you
All right.
later. Thank you.
See you. All right.
Anybody else have a question?